Hey everyone, and welcome to This Explainer. Today we are exploring the fascinating, completely invisible, microscopic world of fish pathogens. If you've ever stopped to wonder how tiny, single-celled organisms can somehow take down an animal that's literally millions of times their size, you are absolutely in the right place. We're going to look really closely at the specialized biology of these bacteria. We'll uncover exactly how their physical structures allow them to survive, attach, spread, and ultimately cause disease in fish. It is essentially a microscopic battle, and it plays out in tanks and ponds every single day. Understanding how it works is absolutely crucial to keeping our aquatic environments healthy. Okay, let's dive into this, because to truly understand fish health, we need to completely subvert our usual expectations right from the jump. When we hear the word bacteria, we instantly think of disease, right? But in aquaculture, bacteria naturally exist everywhere. Seriously, everywhere. They're in the water, in the sediment, chilling on the pond bottom, and they are even living normally right on the fish's skin, gills, and intestines without causing a single bit of harm. In fact, a lot of them are totally essential for nutrient cycling and breaking down organic matter. So the mere presence of bacteria absolutely does not equal an outbreak. To figure out how these harmless, microscopic neighbors suddenly turn into harmful invaders, here's our roadmap. We'll start with the ecosystem balance, then unpack the bacterial invasion toolkit, look at gram staining clues from the lab, walk step by step through the anatomy of an infection, and finish up with a real-world tank transfer case study. Let's start with Section 1 and establish the absolute foundational rule of fish health, the aquatic ecosystem balance. The fundamental equation of fish health is actually pretty simple. Disease only strikes when the delicate balance tips. You've got three main components: the fish, the environment, and the bacteria. A healthy fish swimming in good water quality is perfectly fine, even when completely surrounded by bacteria. But if you introduce an imbalance, say handling injuries, overcrowding, a sudden temperature spike, or maybe low dissolved oxygen, the fish becomes stressed. And when a fish gets stressed, its immunity drops. That environmental trigger, right there, is the true catalyst. That's the moment that allows the normal opportunistic bacteria just floating in the water to suddenly become dangerous invaders. So once the fish is vulnerable, how do these tiny, single-celled organisms actually mount a full-scale attack? Let's move into Section 2 and examine the bacterial invasion toolkit. And this brilliantly illustrates the tactical advantage these bacteria have. Despite being incredibly simple organisms, they are equipped with a highly specialized toolkit. We're talking flagella for movement, pili for attachment, a capsule for armor, toxins for demolition, and biofilms to act as a base camp. Every single one of these physical structures plays a very precise, mechanical role in taking advantage of a stressed fish. Let's break these down one by one, because it's actually pretty wild. First up in the toolkit, we have the flagella. You can literally think of these tail-like structures as tiny outboard motors. They essentially turn these bacteria into microscopic speedboats. Now, not all bacteria have them, but the ones that do are incredibly mobile. If a fish gets a tiny little wound from a net or rough handling, that wound starts leaking nutrients. The flagella allow these motile bacteria in the water to physically swim straight toward that vulnerable site. They use these microscopic tails to actively seek out the damaged fish tissue or suitable sites on the gills and skin so they can begin their invasion. But just getting to the fish isn't quite enough. They actually have to hold on. Enter the pili. These are short, hair-like grappling hooks found right on the surface of some bacteria. Fish have an amazing natural defense mechanism. They're covered in a slick, protective layer of mucus. Without pili to attach firmly, bacteria would simply be washed right away by the water flow or sloughed off by that mucus. But by deploying these grappling hooks, they can anchor themselves incredibly strongly to the skin, the gills, or the mouth, and that is an absolutely critical early step in disease development. Okay, so they're attached. Now the bacteria have to face the fish's immune system, which immediately goes on the offensive to try and destroy them. That's where the capsule or slime layer comes into play. This structure sits completely outside the bacterial cell wall, and it acts as literal microscopic armor. This slick, protective outer coat makes it incredibly difficult for the fish's internal defense system to grab hold of and remove the invaders. Because they have this armor, the bacteria can survive much longer, safely multiply right inside the wound, and really worsen the infection. As those bacteria are multiplying under their armor, they start deploying their chemical demolition crew, toxins, and enzymes. While these aren't physical cell structures like the flagella or pili, they are absolutely vital chemical products that the bacteria manufacture specifically to break down the fish's physical barriers. The enzymes literally digest and break apart healthy fish cells and tissues. they can turn a tiny, barely visible scratch into a massive gaping wound. This microscopic chemical demolition is exactly what causes the macroscopic, visible signs you actually see on a sick fish. Things like severe bleeding, tissue necrosis, fin rot, and those really nasty deep red ulcers. Finally, the bacteria need a secure place to hang out in the environment itself. A biofilm is a tight-knit community of microorganisms that stick to a surface and secrete a protective layer completely around themselves. Think of it as a fortified community bunker. It can form on tank walls, the insides of PVC pipes, pond filters, and even on your nets. If aquaculture equipment isn't cleaned properly, these disease-causing bacteria can survive inside these stubborn biofilms for a really long time. They completely bypass your standard cleaning efforts, and they're just waiting there to spread to brand new, healthy batches of fish. Now that we understand the weapons they're packing, how do we go about identifying them? Let's transition to Section 3 and head into the laboratory to look at gram staining early clues. So the crucial point here is that not all bacterial cell walls are built the same, and the lab uses a really cool technique called gram staining to exploit that difference. The cell wall is what gives the bacteria its shape and a lot of its protection. When a lab worker applies a gram stain, bacteria with one specific type of cell wall will turn completely purple. We call these gram-positive. Bacteria with a structurally different cell wall will appear pink or red under the microscope. Those are gram-negative. Now, it's incredibly important to note that this test doesn't tell you the exact species of bacteria right away, but it is an exciting, vital early clue that helps scientists immediately narrow down the suspect list before they run more complex molecular or culture tests. Let's bring all this amazing biology together. Welcome to Section 4, Anatomy of an Infection. When we map this whole thing out chronologically, the sequence of events is incredibly strict. It always begins with that environmental stress or injury. Once the fish is vulnerable, those opportunistic bacteria use their flagella to swim right over, and they deploy their pili to lock firmly onto the tissue. Almost immediately after that, they deploy their capsule armor to fend off whatever immune response the stressed fish can muster. Safe inside that armor, they start multiplying, they invade deeper, and they release the toxins that chemically destroy the surrounding healthy cells. Ultimately, this microscopic demolition job gets so severe that it manifests as the visible clinical signs we see on the fish, like lethargy, loss of appetite, or those terrible physical ulcers. It's a highly structured domino effect chain of events. To truly cement these concepts, let's look at Section 5 and apply everything we've just learned to a very common scenario in aquaculture, a simple tank transfer. Now, what's really interesting about this scenario is the mystery it presents. Imagine this. You have a totally healthy group of fish. You carefully net them, you move them to a brand new clean tank, and then suddenly, just a few days later, you have a massive disease outbreak with dying fish. Why on earth did this happen if those bacteria were already naturally present in the water before the move even happened? By tracking the exact timeline of the move, we can totally solve this mystery using the bacterial toolkit. On day 1, the simple physical act of netting caused stress, and it probably caused some tiny, invisible scrapes on the fish. Boom, there's your imbalance. By day 2, those opportunistic, motile bacteria use their flagella to swim straight toward those fresh little scrapes, using their pili to anchor deeply into the damaged tissue. By day 3, they're utilizing their capsule slime layers to fend off the stressed fish's weakened immune system, which allows them to rapidly multiply. By day 5, the sheer volume of toxins and enzymes they've produced has digested the local tissue, resulting in those sudden severe red ulcers and the weakened state of your fish. The transfer didn't create the bacteria, it just created the perfect opportunity. So to summarize what we've learned today from our sources, fish disease is a highly dynamic interaction. It absolutely requires both host stress and the presence of bacteria to kick things off. Once that door is opened by stress, the physical structures like the outboard motor flagella and the grappling hook pili make the initial invasion possible. Then, chemical weapons like toxins and enzymes aggressively break down the tissues, leading directly to the clinical signs we see with our naked eyes. And when things go wrong, we can look to the bacterial cell wall through gram staining to give us our very first diagnostic clues in the lab. We've zoomed all the way in today to look at the microscopic weapons these single-celled organisms use to conquer animals millions of times their size. But here's the best part. My understanding that these bacteria are really just opportunists waiting for the right environmental trigger, the power shifts right back to you. So I want to leave you with this final provocative thought. Now that you completely understand their microscopic toolkit, how are you going to manage your water quality, your handling practices, and your equipment cleaning to ensure you never give these opportunists the imbalance they need to strike? Thank you so much for joining me in this explainer, and keep learning.